Welcome back. Now that we understand the underpinnings of what we need in order to successfully do molecular dynamics simulation, we now want to use a higher level programming language, structured programming language like Fortran 90, and now there is a 2000 version as well, in order to calculate some of these trajectories. And we will use that as a sample. And of course, when you get to write a programming code, there are lots of different other programming issues which I am not going to cover, because this course will not get too much into programming side of it, but it will have enough for you to understand the program, so that you can then go ahead and program your own molecular dynamics code. So, if you look at anatomy of a molecular dynamics code is what we will do in this section. And so, if you begin any molecular dynamics code, let us say it is a black box, then some of the things you have to provide as an input parameters, and those input parameters could be number of particles, number of time step for equilibration and EQ, and max KB, maximum number of time step that you are going to integrate trajectories with. Then you give them reduced temperature and reduced density. Essentially, these are the normalized temperature and densities which will allow you to put in parameter irrespective of some of the real units. So, that makes your life easier, because you do not have to worry about real units. They can all be converted later on using the reduced units that you set up. So, if you provide these as initial parameters, number one, what you have to do in your molecular dynamics simulation is to declare all variable and variable types. So, if you look at in any programming language, you will say I am going to call it max KB as the name of the variable for number of maximum time steps, and max KB is equal to 10,000. Let us say I am going to say there are 10,000. So, I declare all that right up front in the program, so that the program knows when they compile this program, that what is the value of max KB. And similarly, you can also define there whether it is a floating point, or it is an integer, or it is a character. So, there are different kinds of variables that are defined in a programming language. So, you also define those, and you may also define certain location of the memory if you are keeping those variables in a vector space. Then you are also going to define some of these variables, and then you can also say some of these variables are common, which will go into different subroutines that you are going to separately calculate, and then they will return the value back to this common variable that is being created here. So, these are very simple programming concept, and with that you can provide simulation parameters specifically for molecular dynamics, like the Lennard-Jones parameter. We talked about sigma and epsilon. These are the two Lennard-Jones parameters of interest that we provide them. Then if you are using fifth order predictor corrector, then you also saw the table of coefficient that I presented to you. You can provide those in the program itself. Those are all the constant values that you are providing. These are static values. They are not going to change, but program needs to have that in order to calculate that. Then you can also define the time step, maximum time step, the time step for the equilibration, time step for calculation of the neighbor lists, time steps for calculation of the properties, time step for averaging of the properties, etc. So, in that you have to start with initial position that we already talked about, that you always start with a position that is known, and as you know, the solid structure is very well known in terms of their three-dimensional coordinate system. So, you start with face centered cubic model, and you can set all the argon atoms, for example, in the Lennard-Jones system of potential energy with the FCC structure. And face centered cubic structure is very well defined. You know where to put the particles in terms of x, y, and z dimensions, and that is where you put them initially, and that is a routine that will be called like init pose, initial position. So, let us say if that is the your subroutine, you call that subroutine, put all the particle location, and then you provide some velocities. So, velocity essentially defined a velocity vector for each particle I in the box, and then those velocity vectors are looked at in terms of the initial neighbor list. So, as you know, you are in FCC, you can calculate the initial neighbor list, and then based on this initial velocity you can also calculate evaluate the force in the system when they are in equilibrium system. So, this is a typical program. C here stands for these are comments. So, you set parameters for argon. So, sigma is 3.405 angstrom, epsilon is 120 in terms of kelvins, Avogadro's number is 6.0225 e to the power 23. Then you have Boltzmann constant 1.38054, and then weight of the molecule. So, you are looking at argon, which is 39.948 mole, and then you are looking at pi, because you are going to be using pi as one of the constant 3.14159. So, with these initial set of parameters, you put that in the program, then calculate dimensional temperature and the volume. So, you look at TR, which is essentially the reduced temperature, convert that into real temperature by multiplying it by epsilon, which is 120. Then volume, which is a particle you are looking at, and the dr, which you are given the reduced density multiplied by number of particles. If you look at number of particles over the dr, which is the reduced density, then you can calculate the volume. So, mass over density and the volume relationship is used here. Now, you can also scale velocities based on 1/3 of the temperature, which is reduced temperature, and then you can also look at velocity over all particles. So, you are looking at sigma and the Avogadro's number and dr. So, now you know the volume cubic centimeter. So, this is the real volume that you are looking at in terms of the sigma. So, with that understanding, now you can set up the system with the input parameters as n, v, t and e. So, initial velocities are r n, and then you have predictor, correct evaluation and corrector. Then you integrate those into T max. So, this is almost like our flow chart. We start with the input, and then we look into velocity, then we you solve the equation of motion, then we average all the trajectory over time, average, and then we create the integrate over T max. So, now we have good average and final configuration and final positions of the particle. So, you start with initial position and then you end up with the final positions. So, this will be an MD code which is written in Fortran 90 2000 initialization comments. This will give you all the idea what different things are. Neighbors, you all start with dAx, x component of the particle in n displacement t is 0. Now, you have epsilon, depth of the potential. You also have kb, current time step, k sort after the time that you sort, k write is the time step at which you write into your file, so that you can look at that. List is the neighbor list, and master list of all interacting neighbors, and then n neighbor is the list that you update every time step. Sigma is the distance where the repulsive portion of the potential is 0, and x0 n, and these are all the parameters related to the fifth order predictor corrector in terms of x position coordinate of particle. So, velocity of particle n, acceleration is x2, second differential, the third time derivative, fourth time derivative and fifth time derivative. That is where the fifth order predictor corrector goes in, and then you can look at x component of particle n position in the previous time step. So, now you already know the previous time step and current time step. So, this is how you calculate. So, I am going back with using this calculation. Now, you can do updating method for time integration, calculate the forces, obtain forces from potential energy, use the Lennard-Jones potential parameter, and then from the initial condition of the crystalline structure. So, this is where we are now getting into the input data. NP is number of particles, NEQ is equilibrium number of steps, max kV maximum number of steps, TR and DR. So, these are the parameters defined either inside the system with a data file that the system would read, or you can interactively put that in as you interact with the program. So, you can also provide those, and the program will ask you what is the number of particles, what is the number of equilibrium steps, what is the maximum number, you start putting in. Now, you are ready to run the program. So, I think this is where the declaration of the variable that I was telling you earlier, that you are providing NPD, maximum particle is 1000, you are looking at all the other number of particles systems, then you are looking at parameter MEC KB skip, how many time step we are skipping, I step, we are looking at the time internal steps. Now, these are the common variables that you can use across different subroutines, and then we are also providing dimensions for the different kinds of parameters, setting up the vectors for them. So, this is the beginning of it, and so now we are looking at the initialization of the program. So, we have already given them epsilon, sigma, the Lennard-Jones parameter. We also give the size of the box. We also set up the number of particles. Now, we also set up the reduced temperature and reduced density. Now, we are ready to run the next step. Thank you.